and I'm using the C operator for them. So if I'm applying C dagger on some scalar psi, and then if I have a vector Ni, Ne, and omega, then by definition, this is equal to that. It's a Kronecker delta Ne0. So if there is anything else apart of the 0, then this is a 0 on the right-hand side. And if it's not, then it's this minus, then I'm writing something epsilon E. I will explain what is epsilon E. And then this is N1 and E plus 1. And this is N omega. Okay? So it only acts, the only thing it only acts if this is a 0, and then it appears a 1. Okay? For anything else, it is automatically 0. So on many vectors in the big Fock space, it's sending them to 0 vector. Okay? Good. And then I'm defining the annihilation operator I. Again, if it's a scalar, if it's a scalar, then scalar is getting out free of charge. And then if it's a scalars, and then it's N1, Ne, and omega, then again, scalar is get out. And this guy is looking here, and it's non-zero only if there is a number 1. So I can write it like that this Ne should be equal to 1. And this is again minus 1 to the epsilon E. And this is making things like that. Ne minus 1 and omega, that's that. Okay? Good. So this is the definition of those guys, and I still need to tell you what is epsilon E. So epsilon E is defined like that epsilon 1 is equal to 0. If E is equal to 1, then this is just 0. And otherwise, epsilon E is defined as a sum of A going from 1, from the beginning, to E minus 1. So you need to know what is staying here. So what is staying in front of these guys, you need to know, and you make the summation of those guys. If it's the even number, then there is minus 1 to the power of even number, which is 1. But if the sum of that is the odd number, then minus 1 to the odd number is minus. Okay? This thing is done there, you will see, to have a Fermi statistics. So this is, if we put these things here, we then automatically have some Fermi statistics into the game. That exchanging of two things is something antisymmetric. So if you will do the calculation also in the Hilbert space with the C operators, we automatically know that we are dealing with fermions and we are not making mistakes. Okay? Without these minuses, we will not get perfectly anti-commutation relations. Good. And as I was telling you, for many of the states in F, so for many of the states in this big Fock space, they simply give the 0. There is only some very small subspace when they are giving something meaningful. Okay? Good. So again, things to check. The first property is, and I will not just make it, I will just write it, but again, as in the previous case, again, CE dagger and CE are Hermitian conjugate. Just check it by yourself, okay? It's easy, something what we did. Great. Second thing, which is automatically from that, we start to explore commutations. And we will see that we will fail with the commutations and we will need to do the anti-commutations. But first thing, which is absolutely obvious if you look from the definition, that if you take CE dagger to the power of 2, 3, 4, or any other higher power, like I'm just doing for power of 2, directly from the definition, you see that for arbitrary vector you take, it's always 0 here. Because if it was at the beginning 0, then first guy will put it 1, and according to definition, the second one should put it to the 0. Okay, and if it was already not 0, then already first one kill it. Okay, so obvious. So this operator is nilpotent. It's called like that. So we can say this is 0 for arbitrary of this vector. So those operators are nilpotent. Okay, so they are like that. Yeah, similarly for the creation operators. So it's like that. So it is like this. Okay, so now let's play with the commutation or anti-commutation rule. So let's see what we will get if we will do the same thing as we did before, and let us apply the C dagger E, C dagger J on some state, which is here. There is some on some position, and E is something, and on some position, and J is something. There are all others are here. Okay. And we clearly see that if here is anything else a part of the 0, then it's automatically 0, right? So the only possibility when these guys can do something is that here is a 0. And similarly here, these guys can do only here something non-trivial when there is a 0. Otherwise it's automatically 0, right? So this is only possibility which we can have. And now we are going to apply it. So this guy is going, and he needs to count all those numbers here, right? And put the factor -1 to something what we call epsilon j. Then it goes, and it makes here on the position nj, he put number 1, and here is like that. Okay? Is that clear? How I did it? Now I'm going with the vector Cj, or this operator C dagger I, and it's again going, and he making out of this 1. But again, he need to count what everything is staying before him, and he put a -1 AE. And this is the outcome of that. Okay? Now we do it in the opposite order. We go C dagger J, Ci, acting on the same situation. Good. So we are starting. So now is going operator Ci, dagger, it goes, goes, goes. He need to count what everything is staying here. He is doing it. And he here put -E epsilon E. Then he meet these guys and place here the 1. Now goes this guy after him, but there is already 1 staying. So what he will find is that there will be a minus epsilon j plus 1, because on the way 1 appears. Do you see it? Okay, and he then put here nj equal to 1. You see it? Tell me. Not yet. So before, Cj was going, he was counting what stays here. He came here and there was a 0, so he counts 0. Continue, 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 and produce the number aj, right? Now this guy is going, but already after applying this operator, what happened? Here change nothing, here appears 1, and here change nothing. So now I'm counting. Plus 1. Here. Everyone see? Who doesn't see? Visit the eye doctor. It's fine? Do you see it? Great. So we now prove it. So what we now get is that, okay, what we get is something, something, so I can now make the difference of those two things or add those two things, because basically what you are seeing here is that this thing together is the same as there is extra minus, so basically there is like writing it like a minus and erasing it from here. So now, instead of subtracting those two lines, I need to add them. Right? Now if I will take C dagger E, Cj, dagger plus Cj dagger Ce, acting on this vector, then I'm getting that I'm having something here and minus something here. So by addition, I'm getting it's directly a 0. Huh? Dagger. Yes. Like that. Okay? You see it? So what we prove here is that first thing which we proved from the definition is that daggers are anti-commuting. And the reason for this anti-commutation is this epsilon symbol. If I will not put it there, then I would have a trouble, or I will not get the anti-commutation. So what we get is that C dagger E, C dagger J is equal to 0. By the similar way, you can now make what happens here if there would not be daggers, if there would be annihilation operators, and here there will be 1. And you will see the same thing happening. So again, you can subtract them. Add them, not subtract them. And you again get a 0. So very easy. We also proved that this is the zero. Good. So the last thing is to prove what happens if now we are having creation and annihilation operator together. And again, the story is perfectly the same, so I can do it also here. So let's do it the same thing here. So let me just erase. Okay. So let me see what I can do. So I will erase. So, oh no, this thing probably will stay. Let me check. Okay, so now I want to do, let's say, CE dagger CJ operator. Okay, and I immediately know that, okay, only chance to get something non-trivial is that if there is a number 1 on the slot number J, and on the slot number E there is a 0. This is the only way how to get something, right? And similarly here, so I'm doing it in the opposite order. So it is CJ, CE, dagger, okay? And again, by the same thing, only non-trivial what I can get is if there is a 0 and there is a 1. Okay, so I'm again going. So this guy is going, CJ operator is going, and it's going. Count the number of occupied state, it's -1 to the EJ. Okay, then it comes here and lowers this number to 0. Super good. Now goes this guy is going 3 times and make number 1 here. Is my calculation clear? Now we are doing in the opposite order. Goes operator CI, going, counts what was here. It's the same thing as was here, so nothing changes. So there is a to the minus e. And now it tries the number 1. So after its action, what happened here is that here appears the number 1, right? Now goes the operator CJ, and it's again counting what happens before him, and it's saying it's almost the same, apart there is 1 electron more. So he says, oh, it should be like that. And he put here 0. Great. And again, you see that this is the same. Before, I should have a plus here, or what I can do is I can erase it, sorry, and I should put the minus here. So again, what I need to do is to make the summation of them. So if I'm making C dagger E Cj plus Cj Ce dagger acting on this vector, it's identically equal to 0. Okay? Good, so at least what we saw is that we are having, so far we also have something like here. And we see that if E is not equal to J, then this thing is also equal to 0. Last thing which we need to prove is put it here E. Okay, and we need to repeat the calculation once more. Okay, so let's do it. Okay, I'm again doing it here. Yes.
So, if I change the index of all the x's of the I,
What? Yeah, but you need to once pick up the order. So you need to take these states alpha 1 after alpha omega once fixed. So this Fock space was defined. I take all the states, I put them to the line, and I need to keep this ordering, how I put them there. I cannot change it from, you can do it arbitrarily at the beginning. Once you say, oh, this is more beautiful state, so I will put it number 1, 2. You put what is 1, 2, 3 up to omega. Once you did it, then everything goes from that point. I don't understand which change you are meaning, but let me finish this, and then we can talk, okay? So here only case, this we don't need to care what happens here. The only non-trivial case here is if there is a 1. Right? And then what we are getting is that, okay, here it appears minus 1 to the epsilon E, because this guy is coming. It counts what happens here, put minus 1 to the epsilon E, and now lowers that to 0. And now those coming the second guy, he goes over all the guys same, so he is getting it 2 times, right? And put it from 0 back to 1. So we end up here. You see? Great. And if we go in the opposite order, here there should be 1. Oh, there should be 0. No, I need to take the same, the state. I need to take the same state. Because I need to compare on the same state, right? So on the same state, if I'm computing it, that this guy is coming, he's C1, is automatically 0. This is minus 1 to the even number, because 2 times epsilon E is always even number, so there is always 1. Right, and I am now seeing that if I'm summing those two things, then I'm getting that C dagger E, CE plus CE, CE dagger is 1. Now you can put here 0, and here 1, and the things will change. Here you will get 0, and here you will get the 1. So it's also true in the opposite case. Okay? So we prove here that if we allow E general, then this is delta ij identity operator. Okay? So we proved it. Good. So what I have more here? No, just that. Great. So now this is the operators. So now, for example, I can have, and now you can ask me the question.
So if you change the order, you will have
Which, why change of order? Epsilon I is just the number of the sum of all the occupations before the given slot. Right.
So if you track specific I,
Yeah, you change the order, but you are changing also the construction of the Hilbert space. The construction of the Hilbert space was like that. I said, take your one particle state, which you know, and order them somehow. I call it like that, alpha 1, alpha 2, alpha omega. How I will make it, it's up to me. What I called 1, it's my choice. What I call 2 is my choice. Once you did it, fix it and keep it forever with you. My choice and your choice can be different. So your fixed space and my fixed space, we need to find a map between them. But they are isomorphic. And that would be exactly plus and minuses which I am taking. And now, give the occupation. Okay, so I will put my ends, you will put your ends. But it can happen that my state 1, 1, 0 can be your state minus 1, 1, 0. That would be only the change. Right? Did you get it? Yeah. Okay. So now again I can have a state 1, 1, for example, a fermionic state, as I did before, for example. So for example, I want to have fermionic state 1, 1. And again, because of this, I can define the vacuum. I can again define the vacuum. Oh, I changed the order. So I can define the vacuum again as a state which is annihilated by all fermionic operators for all E from 1 to omega. And then I can define my fermionic states. Like I will call them F, which I need to now specify all the creation operators, right? So I can take C1 to the power of N1, C to the power of N omega, acting on the vacuum. And this will be the state which has these occupation numbers. But basically, since we show the properties that these C's are nilpotent, so only meaningful possibilities here are zeros and ones. So you cannot have nothing else here. Only 0 or only 1. And then you will get some zeros and 1. Okay? So for example, this will be now the case where is the information about the statistics. So I can take the state Psi, which would be C free dagger free, C dagger 27, acting on the vacuum. In the occupation basis, it will look like that 1 and 1. Okay? But I can also take the state C dagger 27, C dagger free, acting on the vacuum. And in that case, I will also generate the state 1. But when I want to generate the state 27, I need to put a minus. Okay? So now you see, like, This is a different state. Yeah, so this is the one vector and this is the minus vector. Okay, both of them have 1 and 1, but this minus sign is now encoding some information which state was occupied first and which second. Okay? You see it? Okay? Fine. And now we start to calculate the matrix operators or particle operators, like using the creation and annihilation operators. Okay? So these will be the things which we are going to do. Okie doke. So this was that. So now we have the operators which are acting in the Fock space. We somehow know how to calculate with them because it seems to be nothing super difficult. So now let's start to do some operators with us. Good. Guys, do you have question? Because I'm now going to paragraph 3.4 about one-body operators. Can I go on? And I will just write the solution. I will not prove the solution. Proof of the solution is make this. Go from that, use the equation hard, write the operator, use the equation hard, and get the result. Okay? Which is like, okay? And it's just the combinatorics at the end. Actually, I didn't find a good book when it's good explained. It's always like explain, and at some point authors get tired and say, one can see that is that. Okay, so I don't want to break tradition, so I'm also doing like that. Great. So, once I was on the lecture of one mathematician, and he was explaining one principle, which is called like the Jacobi principle in classical mechanics. And if you look for many books from classical mechanics, Landau, Lifshitz, or many others, it's always explained that you don't understand it. And then he said like that, in many excellent books, it's always explained such that no one can understand it. And I don't want to break tradition, so I will also explain it like that. But he did a great job, we understand it at the end. But I like the story that, yeah, he was right, like, in many books which I know, it was Maupertuis-Jacobi principle, it was called, Maupertuis principle. Maybe you heard in the classical mechanics there is something what is called Maupertuis principle. Good, so let me drink the water. And let me do the story with the operators. Okie doke. So in principle, so if you have a one-body operator T, and you know what I was telling you before, that you take some state alpha, and you know to which state is this state going, so it means this state is going to some superposition of states beta, T beta alpha. Yeah, so it's a linear operator, so you map a vector. Then I told you only what you need to know is to compute these guys, which is abstractly written like that. It's a scalar product of these things, right? I'm using this Dirac notation. Are you fine with that? Well, if you will not, we are in loss because I don't know how to explain it without Dirac, but I hope you are fine with this. Are you fine? Some fingers up, I like it. Very good. Some eyes are saying yes. Good. Great. So then in principle, abstractly, and this is the proof what I want to say. So abstractly, the operator T, I can just write that it's the sum over alpha beta. This is the one particle state, and I can write it like that. It's a beta T beta alpha acting on the alpha. Right? This will be the, how I will write this operator as an operator. Great. And now the question would be, okay, so from the states alpha, we have wave functions. So if you are in the R representation, that talking about the state alpha, we are talking about the wave function of that, which is some wave function alpha r. Talking about the beta, we are talking about the wave function beta, which is some beta as a function of r. Talking about some operator, operator t is something which acts on the position, or it's a derivative, or it's a higher derivative. Simply it's some differential operator which acts like that. And the matrix elements which we will compute, t beta alpha, if it would be in the R space or in the wave function representation, would be integral over R. Yeah, d-dimensional in principle. This depends on the dimension of VR. And what I need to do is I need to take the wave function beta, make a star of it, right? And then I need to apply my operator t, which is the differential operator, acting. I have a problem with gravity. Acting on alpha r, right? This thing is how we will compute it in the quantum mechanics. Yeah, this would be the matrix element. So you see, so that's exactly what I'm doing. I take state alpha, which was the abstract state, I make out of that the wave function. I know if I have the wave functions like that, and now I would like to write it in the... Then I told you how to do it if I have many states. I was also telling you how to make it if I have a many states. So T acting on many states. Was like that act on each state separately. Yeah? So we say it's like T acting on alpha. Yeah, it was at the beginning. All others unchanged. Then move to the next guy. Maybe it's better to display like that. Then alpha 2, right? And all other untouched, etc., etc. And the last guy is this guy. T acting on alpha n. Great. So and now symmetrization means I need to symmetrize or anti-symmetrize at the end here. So if I really would like to know how to symmetrize, then I need to apply PS or PA on that, and then I will get how it is on boson or fermions. Oh, yeah. And this is these things which I was telling you. Okay, we are applying this equation star. So now we can start with this vector, which is the generic vector in the Fock space. So this is something in the Fock space. Now I am using equation star, and I am transforming it to such wave function, which would be the wave function which depends on many indices. So I am writing it. It would be psi, depending on n variables. If the sum of all those guys is equal to capital N, then it will be some n-dimensional wave function, which is symmetric or anti-symmetric. Okay. Now I take my T operator, and this T operator, which I am doing, is basically like that. So this T operator is like this. So before I have one operator, just I want to tell you. So before I had this operator T, which was just depending on the one coordinate. So now, if I'm extended it to be things acting on the n-dimensional wave function is like that. That is the operator T acting on the first coordinate. All other is identity. Plus identity. Now it's the operator acting on the second coordinate. Again, identity, all or others. Plus, etc., 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 up to it doesn't do nothing with the first n coordinates, and on the last coordinates it do something. So this is this extension from single particle, which I know it as a differential operator, acting on one wave functions, how it acts on many wave functions. It basically extends like this. Okay? So now we need to transform it. Now we need to apply and transform it back. This is this procedure which I am telling you about. Yeah, this was this picture which I draw on one slide. Okay. The answer of that is, you can do it, and I will just write the answer. So this T operator, if I know all those matrix elements, it acts in the Fock space in the following way. is the sum over alpha and beta, and this is C dagger alpha, or let's call it like, okay, alpha beta, but let's write C dagger beta T beta alpha C alpha. This is all. Or A dagger, so it's for fermions, it would be like that. If it's for bosons, it's the same. You just need to do that. This is the outcome of all this game, like a big circle, which you will make it like that. Okay? For the one particle operators. One particle operator means like, okay, it's an operator which in the Schrödinger representation is some differential operator. In one variable is like that. In many variables it's like this. It acts on this wave function. Yeah. Do you understand it? What I'm doing here? Guys? Yes or no? You show it like that, so I said, I did. I even changed the space. Yeah, but this is like that. If you have, let's say, how you solve the Schrödinger equation for two particles. For example, you know that operator of the momentum acting on one particle state is h bar divided by E, and there is a gradient with respect to the variable r, right? This is the momentum operator. Now assume I have a two-particle system like hydrogen atom. What is the momentum operator for the hydrogen atom? So I have a wave function which now depends on two positions, R1 and R2. And if I would like to know how the momentum P acts on this wave function, that's basically what I am doing is that I am making h bar divided by E gradient on the first component. Second component is untouched, which I just try to visualize that I am putting here identity operator. So there is nothing happening on the second coordinate. Plus, it would be h bar divided by E. And now I need to make the derivative with respect to the second argument. Right, so this is how the momentum operator works on the two-particle system. So this is like that. So this and now this. If you have more particles, then you go similarly. Okay? So this is this extension which I was doing. Again, you write it as a wave function. So this is some other wave function which you can write it as a phi, R1 and R2. And now you need to chop this wave function in terms of the equation star and distillate which N1 and N2 and which coefficients are there. But the answer is you can also do it directly like this. Okay, this is I'm making just the claim. Do you understand that the claim which I'm making, I didn't prove it, I just claim it, it would be this. But you understand the story, how we need to do it? That's important for me. Understand? 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 Great. If you're lying me, you are lying to yourself, okay? So just be sure that you understand. Great. So what you see, what we really, many things just need to do, we just need to compute these things, such kind of the integral. If you have something in the Schrödinger quantum mechanics in the position space, and you want to convert it to the creation and annihilation operator in some abstract Fock space, basically you need to compute such things. This is only the complication. And then you just make some expression which like that. So let me give you some examples, okay? So we will do some examples. Okay, how much time we have? We don't have time, right? 2 minutes? 8 minutes? God bless America. Okay, so then let me try to do something. And for you see, for boson and fermions, sorry, I wrote it so sloppy here. But for boson and fermions, there is no big difference, basically. You just need to do like that, and you put fermionic or bosonic operators. It's a one-particle operator. It doesn't care about the rest, okay? So it's not two-body operator, so there is not a big difference about the statistics or something like that. Good. So let's make one simple example. Okay, so what I have? We already saw it. Example. But we will need it several times, so it's important. It's a density operator. So in the Schrödinger case, when you have the wave function psi, and if you would like to know what is the density of the particles at some point r0 which you pick up, then you know that this is nothing else as a psi square computed at point r0. Right? So this is my operator which I would like now to transform to the second quantized form. Okay, so I need to write it, or if I want to write it, so basically I can write the same thing in the following way. You remember, I need to write it as some d-dimensional integral over r. Okay? Now I need to put psi star at r, I need to put psi at r, and I need to put here some differential operator, such that if I am working it and integrating, I will get this number. Super easy, right? Delta function r minus r0 is doing this thing. Right? So I see that the density operator in the Schrödinger picture is just delta r minus r0. Great. So let us assume I have particle in the box. Okay. So what I'm having here? So I'm taking my Fock space. Guys, can I finish this and steal from your time? Okay. Dani agree, and that's enough. So if one agree, no, who needs to leave then? Okay. So this is my Fock space, and let's say I am considering the particles in the box. Okay, so this is my states, which are the eigenstates particle in the box. Okay. So if I am taking the wave function of that, so those things are labeled by the momentum k, and if I'm doing it one-dimensional, it is 2p divided by n times some integer number. Yeah, this is the thing. Oh, 2p, it would be like L. If the length of the box is L, then it would be like that, yeah? So I know that if I really take any functions like that, alpha k, that by definition from quantum mechanics I know it's 1 divided the square root of the volume. Okay, in our case it's L. If I'm doing it one-dimensional, and it would be a to the e k n times f. This would be my eigenstate. Okay? So I am now having my occupation numbers. Great. And what I just really need to do is, so what I'm exactly doing. So I take these states, I need to transform them to the R representation, which I did. And now I need to compute these matrix elements. Okay. So if I really want to compute beta T alpha, this was the integral, dr. And now I need to take the wave functions for the state beta, which is 1 over square root of the volume. Let's say beta is a to the minus e k beta r, okay? And it's a minus because it's complex conjugation. Now I need to apply the operator in the Schrödinger picture, delta r minus r0. Okay. Now I take the state alpha, which is a to the e k for the state alpha r divided by the square of the volume. Okay, and I'm just integrating it, which is easy peasy. So I'm getting it's 1 over volume e to the e k r, e r0, and this is k alpha minus k beta. Like that, okay? So this is this matrix element. Great. So how this operator, density operator, now will look like in the creation and annihilation operator. So I'm writing density operator at point R0. R0 is my point which I'm picking, okay? It's a parameter, it's a variable, it's a something parameter of my operator. Operator is here. So I know what to do. It's the sum over alpha, sum over beta. Alpha, beta are just these quantum numbers, kn, km. So the sum over alpha, beta is the same over k alpha and k beta. This is my state. Then I'm writing the annihilation operator beta for the state k beta. Matrix element, 1 over volume, e to the e r0, k, what I will get, k alpha minus k beta, right? And this is c, k alpha. That's it. Or a. This is for fermions, I wrote it. For bosons, it will be just a. Okay? So now you write the density operator in the second quantization, assuming we need to know that the basis of all the wave functions are to the eigenparticle basis of the particles in the box. If you take the hydrogen atom, then you will need to compute this for the wave function which corresponds to the hydrogen atom, which will be some Lager polynomials and spherical harmonics. And then you need to again compute such elements for such things, okay? If you change the Bloch wave function, then the Bloch wave functions are labeled not just by k, but also the band index. So again, you need to write this expression, which is some expression of the wave functions, and you need to calculate this integral. So things will change, but now this has a meaning that this is annihilating the state with the momentum k alpha, and this is creating the state with momentum k beta, okay? Did you get it? And then you will have something annihilating Bloch electron with K and creating another Bloch electron. Or hydrogen electron in the state LMN and creating another electron in L prime, M prime, N prime, okay? So this depends what is here, what we choose. So I choose particle in the box. If you choose Bloch, or this depends on the system which we are solving, this I told you, yeah? This was the abstract stuff. Okay, so this is one thing. Another thing which I want to do, but then I will put it as a homework, is let's write what will be the current operator. We know the current density, so just to make, this is the last minute for me. So we know that in quantum mechanics we can compute the probability current, right? So if I have a state psi, I can compute what is the probability current. And the probability current is h bar divided by 2me. Oh, but I need to go because I have a meeting. And it is a psi star. And again, I can compute probability current at some position R0. It is psi star at point R0. And there is the gradient of the function psi evaluated at point R0 minus function psi at point R0. And this is the gradient on the function psi complex conjugated evaluated at point R0, right? So this is the probability current. It's in the Schrödinger representation. The question is, how will the probability current operator, this is just the parameter of the operator. Operator is here, this is the operator. Changing that, how this will look like in the second quantization if we again go to the plane wave basis. So again, what you need to do, you need to write it in such a way that here is some sheet which depends on R, derivative of R, and many other things. Then you need to take this sheet here and do this integral. That's it. It would be done. Do you see the logic? Great. That's all. So next week you are solving the problems. If you have a problem to solve the problem, let's make appointment. We can maybe talk someday, Wednesday or something. Just write me email. But ideally, if you together try to solve it, and if you are some collective group have a problem that I don't have 27 individual meetings, but rather one meeting with 27 people. Do you understand what I'm saying to tell? What I am trying to tell? Okay, that's it. Okay, and now I need to hurry up.